Hear all this? Anytime you're asked to find the gravitational potential energy, it requires knowing three things. But I say that I'm assuming you're calculating it directly, because I'm pretty confident I can ask for this in a number of ways without you having to calculate it directly. Now, not knowing the question, so they say it's a 55 kilogram person. So that would just be 55 kilograms times, they want 9.8 times 0.5 meters. That's all you had to do. That's it. So I don't know what that is when you multiply it all out, but that should be the answer. They might have mixed the mass. So I don't know what your mass was on your version of the problem, but it'll be something around there. Any other question on homework? Yeah. What? 10. Yes, 10? Yeah. 10. This one is worth paying attention to. I was expecting this one. We hadn't had a chance to talk very much about the energy stored in a spring. Of course, my response to that is probably not what you want to hear. Something about, you have access to the textbook where there's instruction. But let's say that for the next few moments, what I talk about right now is something you might want to put in your notes. Look, springs store energy kind of the same way that gravity stores energy. There are a few distinct differences, and we will talk more in depth about them, but probably not before the test. Therefore, the in-depth part I won't put on the test. But your ability to be functional with this, I would put on the test, since there's just not that much here. You can treat it like any other form of energy. So the way the problem is stated, there's a spring launcher. And in order to launch something on a spring launcher, you are going to pull back the spring, place a ball on it, and then release it so that the ball will leave the launcher with some launch velocity. Of course, in the continuation of this problem, the ball makes it to some height, they say y, above the launcher. Now, I think there's not a person in the room who hasn't played with a toy that does something like this. If it's the car that you pull back, let go, and it shoots across the room, whether it's the launcher that launched a little Hot Wheel car, there's plenty of toys that use a spring to launch a projectile, a ping pong ball, or a little rocket. And although maybe not all of you had something similar, using a simple spring to add energy to a system is mostly in most basic toys. So I'm going to assume that this is not asking too much of you to think about. The fact that it's all vertical, though, does play a role in shaping the answer to this question, so I would pay close attention to this next part. First, when it comes to any energy where an object's going to change height, this is a note, by the way. When it comes to any type of energy or situation where an object's going to change height, it is best to establish what the lowest point in the problem is, for that is the point to which you should pay attention to gravitational potential energy. What I mean by that is, this is the lowest point in the problem, not the top of the spring launcher. So when the spring launcher is pulled back the 25 centimeters, which is, of course, 0.25 meters, this represents a 0 for potential energy. At this moment, all the energy is in the form of potential energy, but this is elastic potential energy, which I'll come back to in a minute. But it's still potential energy. The energy is stored between the object and the spring. When the spring is released, the spring pushes the ball, doing work on the ball, changing its kinetic energy, so that here the ball has kinetic energy. But is the ball above its lowest position? Well, because it is, of course, above the lowest position, it also has gravitational potential. Not very much, maybe even a negligible amount. But if you really want to know how this works, you need to take that into consideration. I don't know if this problem does or not. I'm going to assume it does. When it makes it to its maximum height, all of the energy is now in gravitational potential. But again, y isn't the height. Y plus 0.25 is the height. Because the lowest position was established when we pulled the spring back. With that being said, all of these points of energy have to be the same value. So here when the ball's at the max height, the energy is all in the form of gravitational potential. Any question about why I wrote that way? Here, when we're just leaving the gun, it's all in the form of kinetic and a little gravitational potential. And here, in the gun, it's all in the form of elastic potential. Now, we've not had a chance to talk about elastic potential, but there's not a whole lot here. Elastic potential is 1/2 times k times x squared. And I'll explain what each of these is, but I think one of them is pretty easy. X is how far the elastic is stretched or compressed. Bless you. How far the elastic is stretched or compressed. K is what's known as the spring constant, sometimes called the Hooke's law constant. It's how strong the spring is. You can tell in a problem, it's in newtons per meter. That's the unit of the spring constant. It's how much force you get per meter of compressed spring. I'm confident they probably gave us the spring constant in this problem. I don't know what it is, but I'm confident they gave it to us. So, without further ado, let's work the problem. Let me see. They tell me the spring constant is 667 newtons per meter, and the ball has a mass of 1.5 kilograms. So your variables might be different, but that's what I have for mine. You guys ready to work the problem now? All right, so to make this a little easier to see, there we go. Let's work the question. They want to know all of these things, so I'm just going to work it one at a time. Starting with the amount of energy in the system is 1/2 times 667 times 0.25 meters squared. That's the elastic potential energy. Question number 1. Find the muzzle velocity of the gun. So that's going to be how fast it's going when it leaves the spring gun. Find that here. 1/2 m v squared plus mg h. Any question about where I got any of those values? Okay, you guys can find v. I don't think finding the number means very much. So the next question asked, what is the highest point that it attains? I don't need anything I've just done for that. I still know that this is the amount of energy in the system. So 1/2 k x squared equals m g h. Again, I'm trying to figure out how high above the gun the ball makes it to before it comes back. I'm just solving for y. So if I assume that the suitcase was lifted up the 0.8 meters that they're talking about here, that's a pretty bad suitcase, but 0.8 meters, 16 kilograms. The work done in lifting the suitcase would be equal to mg times 0.8, or 16 times 9.8 times 0.8. That's how much work was done. It'll be stored as gravitational potential energy. Now, just holding it, how much work is done? None. Holding it there, I mean, it might be hard for you to hold something in place. You might feel like you're utilizing energy, but you're not doing work on the object. It might require energy to make your muscles stay contracted, but that doesn't mean you're doing any work on the object. So question B is misleading, but intentionally so. So in that case, zero work is done because the object's not changing height, or you're not changing its velocity. Question C, what work do you do when you lower it 0.8 meters? Probably the negative of this. Now, that part might not be obvious to you, but if we consider that you are pulling upwards on the object, and the object is being lowered to the ground, then there is an 180-degree difference between the direction the object is going and the force you are applying. By lowering it to the ground, the reason you do negative work is you are preventing the work done by gravity from changing its kinetic energy. You could just let it go and it'd fall right to the ground. It'll still make it to the ground, but it's going to hit the ground now at some velocity. You doing negative work prevents the suitcase from accumulating that velocity and perhaps breaking something in the suitcase. Leave it to the airport guys. They'll throw it around for you. Yes, sir?
25.
Reading passage problem. I don't want to read. I'm not even sure I ever learned how. Oh, there's a whole lot of ready here. I'm not doing it. That's a lot of ready. Somebody boil it down for me? Yeah. All right, I'm just going to read what the question says, see if I can figure out what they want. I figure that's all you guys ever do anyways. Did you read the whole paragraph? Who made number 25? Oh, heck. Nobody did. Suppose that the net vertical impulse on the 50 kangaroo due to all external forces is 100 Newton seconds. Find its vertical component of velocity when it leaves the ground. Assume that the kangaroo is initially at rest. Yeah, I'm going to have to read the whole thing to do that. We really don't have the time for it. So, perhaps tomorrow. All right, last one. Yeah?
17.
17? This one has a lot of read on it, too. I'm not going to do it. I want you to know that. Mr. Shelton doesn't know how to read. Oh, I can read this one. It's like 2 sentences. Good. It's in my wheelhouse. A roofing shingle elevator. Ooh. They're doing the roof here. I swore some guy was about to fall through it earlier today. I'm taking my tiles down today. If anyone wants to come after school to help me, I'll give them service hours. I have to get my roof replaced at my house, too. It's like $13,000. All right, a roofing shingle elevator is lifting a 25-kilogram package to the top of a building at a constant speed. The angle between the elevator track and the horizontal is 75 degrees. The power of the elevator, I was hoping somebody finally asked me about power. 700 watts. This might be a good thing to write down. You see, sometimes teaching needs me to explain something new, but sometimes it's better to just have application. Power is one of those things. Power is the rate at which work is done. It could also be said it's the rate at which energy is consumed. For example, a light bulb doesn't do work, but it consumes energy. That's why it's rated in watts. So a 60-watt light bulb is consuming 60 watts of energy. All of these are a rate, which means that power, by definition, being a rate, will be a something per second. So times on the bottom. On the top has to be something with energy. So there's any number of things that could be on the top. Work being the most obvious. Power is work over time. But it could also be change in kinetic energy over time. Or energy over time. Or change in potential energy. Any one of these can be considered power, since any one of them is the rate at which energy changed. Now, a little bit of station keeping here would be to let you know that that's got to be in joules per second, which is a watt. W-A-T-T, after James Watt. I don't know what he did. Probably something with watts. Now, I want you to understand something very critically important about power. The word power and the word powerful don't have anything in common. Please understand that. Having a lot of power doesn't mean you're strong. And I don't mean you personally. If you have an engine with a lot of power, doesn't mean it's applying a lot of force. I would write that down. Again, having a motor that has a lot of power doesn't mean it applies a lot of force. It means it does work quickly. A more powerful car doesn't necessarily pull harder against the ground, but it gets up to speed faster because it changes something's kinetic energy faster. But it doesn't mean it pulls harder. You need to be careful about what we think when we think power. It's how fast work is done. Now they're telling me in this problem that the elevator has a power of 700 watts, and it's lifting a 25 kilogram package to the top of a building at a constant speed. Now there's a lot to unpack in this problem. It says the elevator has an angle of 75 degrees. The package of shingles, 25 kilograms. It says determine the vertical component of the speed with which the package is moving up, assuming no friction is exerted on the inclined surface or the package. I can think of 3 ways we can do this problem. 3 ways. So here's the way they would like you to do the problem. They would like you to use this relationship to do this problem. And They want you to see something about this relationship. Okay. Any surprise there what I did? We all following along? You know, I can put my parentheses wherever I want. So here's the order to which I will do this multiplication and division, because I can multiply and divide in any order I want. Now, if you're paying attention, you'll realize that by putting this together, that's velocity. They just combine two things together on you. So power 700 has to lift the weight 25 times 9.8 times the sine of 75 degrees. Right, the angle is 75 degrees times V. That's how you figure out how fast it's going to go. There's a lot there. And I'm okay with you having to struggle a little bit with this one. I'll remind you of all the things that are there. F represents the force required to lift the object. It's going up a ramp. So that's mg sine theta. mg for the package is 25 times 9.8. The angle they gave me was 75 degrees. That's the force necessary to lift the object. They tell me the power of the motor is 700 watts. So how far they move it divided by how long it takes to get there is how fast it's going. That's why they're asking for the velocity. You would not have been expected to be able to do that problem for homework tonight. We were going to talk about stuff like this today. Power is not on your test on Friday in any meaningful way, except for knowing that definition and knowing that unit. Yes, sir.
So previously when talking about work, we used cosine theta because it was horizontal, but this problem wanted us to use sine of theta?
No. Guys, pay attention to this. Let me go to a new page for this. Clearly, you're not having your quiz. It's mostly because somebody was so worried about it today, they were having a bad day over it. It's not true. I just want to be able to answer questions about homework. Now, look, some of you are not going to get this, and I'm sorry about it. You're just not good math students. Okay, but pay attention if I were you. Either way. If I want to push a box up the ramp, at this moment, my expectation is that you guys understand the force required to push something up a ramp means I have to work against the component of the weight down the ramp. Everybody understand that? So that force would be mg sine theta. And perhaps I would push the box a distance delta x along the ramp. And so the work would be mg sine theta times delta x. Okay? The work done by gravity would be mg sine theta times delta x times the cosine of 180 degrees. That'd be the work done by gravity, because the work done by gravity is the work done by this force as the object moves up the ramp. Two different amounts of work. We've talked about that, but not on a ramp before. Yes, ma'am?
So what was the first work?
The work done you do pushing it up the ramp. And the other one's the work gravity does against you pushing it up the ramp. Now, follow along, kiddies, because this is the meat and potatoes. This is why you do so bad in your math class. The definition of work is force times displacement times the angle between them. I could not consider components and consider the fact that mg acts down, but the box is moving up the ramp a distance delta x. If I want to calculate the work without breaking into components, which I'm allowed to do, it would be mg times delta x times the cosine of, what is this angle? It's not theta. Do we know what that angle is? Yes, ma'am?
180 minus theta?
It could be 180 minus theta. That's going to work. So 180 minus theta. There's also another way to write it. It could be mg delta x times cosine 90 plus theta. Now, you guys are in pre-calc, right? So you're learning all about trig functions now. What you probably either don't know, haven't learned, or forgotten is that cosine of 90 plus theta equals cosine 180 minus theta and equals minus sine theta. Now, I don't know if you've learned this or not in your class. You would have learned this if you have learned that cosine of a plus b equals cosine A cosine B minus sine A sine B. Have you learned that yet? You will. Some of you have. And if you haven't learned it, look, this is why I didn't teach it yet. But all of that is true. And if you're really paying attention, you realize that means both of these are just mg times delta x times minus the sine of theta. Right? Same. You just get the same thing. Negative mg sine theta. All right. Bye-bye. Usually is a lowercase k. For classroom kind of stuff, things that you would probably interact with in the classroom. Oops. You'd probably have spring constants that are in the hundreds, maybe the low thousands. So to get maybe 600 to 1500. The unit is newtons per meter. And that shouldn't be a big surprise. How many newtons to stretch it a meter? And to put Hooke's law, which tells you how much force it takes to pull out, push in a spring, it's proportional to the displacement. That's what it looks like mathematically. This is a vector, though. And this is a vector. So to make sure that we get the vector part right, we need a minus sign there. Because this is all relative to the spring. So if I have a spring attached to like a little piece of wall, if I want the spring to be pushed in this distance x, what direction will the spring push back? So you get the idea that if I push inwards to move the spring this way, the spring is going to try and push back outwards to restore itself. That's why there's a negative sign here. If the spring was pulled outwards, it would try to pull back inwards. So this F is with respect to the spring. We call this a restoring force. There are lots of things in nature that restore themselves to their original shape. We can store energy in this. Anything that wants to restore itself to its original shape, we can restore energy in it. When we deform it, when it tries to pop back to its original shape, you can get the energy back out that you put in deforming it. And bouncing a ball does that. When you bounce a ball, you drop it on the ground, it deforms, then it pops back, you get back the energy that was stored. So all these objects store energy, and the amount of energy is stored as elastic potential energy is equal to 1/2 kx squared. K is the spring constant, and x is how much you deformed the object. Teachable moment. Let's talk about the spring launcher question, okay? Spring launcher question has, in my view, I guess 3 parts. And I think this is how the problem is also set up. There's keep thinking they're going to crash right through, right on top of us. How many of you know what I'm referring to? The roof people. Don't even try and walk quiet, but I mean, why would you? You're a roof person. The roof people. They're coming to get us, the roof people. So, there is the fact that in its relaxed state, the spring looks like this. Part A of the problem, the spring has been pulled back 1/4 meter in the launcher. You guys realize this is a little toy we had, right? We shot the ball for our little projectile thing. This is exactly what we're talking about, the same thing. Put the ball there. When released, the ball would come away from this with a velocity right here. And then came to rest someplace way up in the air. Can you guys imagine these 3 parts of this arrangement? So let's kind of start here at the beginning. In the beginning, I'm going to state unequivocally that right now the ball is at its lowest position. Would you guys all agree that at this state, and when I say state, I mean right here, A, is at its lowest position, B, it's a little above that, and C, it's way above that? I'm saying this to establish what we're going to call 0 for the entire problem. We said that gravitational potential energy requires a reference level. This is my reference level. I'll say H0, the lowest point in the problem. This will be the 0 of the problem. Is everybody okay? Any question about that? All right, in part A, can we all agree the ball has no gravitational potential energy? Because right now it's at the reference level. Now just, if you haven't kind of put this together yourself, there are 3 kinds of mechanical energy. If you believe your system is isolated, then the energy is always going to be bounced around in these 3 kinds. So right now I'm asking myself, at A, does it have gravitational potential energy? So if it's not above the reference level, the answer is no. Does it have elastic potential energy? If it's touching a spring, it might. So I'm thinking here, probably. Is it moving? that it has no kinetic energy. If you go through that line of questioning, you can probably isolate the kind of energy we have at A, which looks like we have elastic potential energy. Are we good there? Because we're going to go on to part B, or thing B. Let's consider what's going on at B. Starting at the top, is the object above the reference level? It is. Is the object pushed back against some spring? I don't think so. It's leaving the spring here. So no elastic. Is the object moving? Yeah. Excellent. And now on to C. Is the object above the reference level? Sure is. Is the object moving? No. Not if I'm talking about the max height. Is the object storing elastic potential energy? No. It's no longer touching a spring. The big takeaway, all of these have to be equal. If there's nothing there to take energy out of the system, then the states of the system all have to be the same. They have to have the same amount of energy. They can move in between all three, but the total has to be the same. So at C, we're told that's Y. So the amount of potential energy here, mg y plus 0.25. Right, the height is from here to here. Any question about that? We sure? We're good? So I think you guys would have missed that, if it was a test question. In fact, I think your book wants you to miss that. I'm not sure the book does a good job of this. I think the book wants you to gloss over that there's energy going from the compressed spring to this point. I think the book might have even forgotten that in their treatment of this, but it would be on the AP exam this way. All right, this next section, it's 1/2 mv squared for sure. But the gravitational potential energy that's here, mg times 0.25. Again, that might be really small. Maybe a little tiny bit of energy, but it's still there. And last, our first time using this, 1/2 kx squared. But we know x, because they tell us it's pulled back 0.25 meters. Again, all of these have to be the same. Now, in my version of the problem, and they might have scrambled the numbers, they told me that the spring constant was 667 newtons per meter. So I have, for the energy, 667 times 1/2 times 0.25 squared. That's how much energy is in the problem. I believe the ball was 1.5 kilograms, which, I'll be honest, pretty heavy ball. I'm not sure you want to, 1.5 kilograms, that's kind of a lot. Might not seem like a lot, but I throw a 4-pound ball at you. Be ready. So that'd be 1.5 times 9.8 times 0.25 plus 1/2 times 1.5 times v squared. Looks like I can figure out how fast it's going with what they gave me. Again, what that actual number here is, not very interesting. Just trying to show you how to do it. Now, they also wanted how high it went above the launcher. Look, you could do it independently. This is the amount of energy in the system. So I don't have to find the velocity to figure out how high it went. I can say 1/2 667 times 0.25 squared equals mgh. Once I know one state's energy, that's the energy for the whole problem, unless something takes the energy away or adds to the energy. Now, you guys can do the algebra. That is the least important, the least interesting part. I want to know that you understand how the energy is related. In this problem, the elastic force gives energy to the ball by doing work on the ball. At the same time, gravity takes a little bit of that energy away, but changes the ball's kinetic energy. The ball then rises into the air as gravity does work to slow it down to a stop, taking away its kinetic energy. That's how it gets to the highest point. Yes, ma'am?
Do any of those equations change if the reference point is someplace else? Because I thought it said that like where y is equal to 0 is at like the top, like where the ball is at B. Does that change anything?
If they said that the reference level is considered where the muzzle of the launcher is, it would not change any of the answers. If I do that, I know it moved everything else up, but I think we have enough here I can go through it. Then bear with me. This, let me get a different color here. This would not change because it's not related to the reference level. The only thing that relates to the reference level is gravitational potential energy. This would essentially be 0. But this is where the book I think is doing you a disservice. And here's why. All of this energy did not go into kinetic. Some of that energy lifted the ball. Not much. The book is having us leave this out and saying, okay, now we're at the reference level. This is why when you're a test writer like I am, you don't do this problem if you don't want students to know that this change in height doesn't really matter to you. And there's ways they could have gone about doing that and eliminated that as part of the problem, but they didn't do it that way. And look, the AP exam is going to expect you to know the difference. So when they reset that, unfortunately what they did is they meant that over here, we should have accounted for the fact that we're below the reference level. But I don't want to do that for you guys because that suggests that gravitational potential energy can be negative and that we have to get up to 0. And that doesn't make any sense to me at all. And I know a lot of things. So I always say, figure out where your lowest level is. Work from there. This problem is not a good example of it, but it's the only example they provided in mastering. So I had to use it. Now, just so you guys know, if I was to do this problem, and I didn't want to try and trick you into remembering that. Because I think a lot of students would have, if I had taught springs yesterday, I think a lot of students would have not thought about the change in height inside the launcher. And I'm used to that having worked with students before. So if I want to not trick students, but still see if they understand how this works, all you have to do to eliminate that as part of the problem is be very careful and patient about how you set your problem up. So you put the launcher on the side, like this, and you put a curved ramp at some point. Now, when I pull this back, if it's the same question, when I pull this back, I will have elastic potential energy stored in the spring. When I release it, the ball will have just kinetic energy because the ball never changed height. I'm pretty good now. I'm okay with that, right? No change in potential energy. And now the ball, if there's no friction, can be shot up into the air, and now I have gravity completely separate from the other kinds of energy. All they had to do was put the spring on its side. They didn't do that. So we need to take into account that amount of energy. Now, they made the spring strong enough where that amount of energy was actually pretty small. The change of gravitational potential energy really didn't affect the problem very much, but it did affect it some. But do you see how this problem is different? and how I wouldn't have had to worry about the gravitational potential energy here because I just shot the object sideways towards a ramp which projected it into the air. This was last year's test question, just so you guys know. A launcher like this, some form of it. And just so we're all clear, this problem and this problem, largely the same. You understand why? Let's talk about it for just a minute. What if I asked you how high along the ramp the ball goes when launched from here? When the ball goes up the ramp, it's still going to have gravitational potential energy based on how high it is above the ground. It doesn't matter that it went up a ramp. If you don't believe me, we should run the math on it. And I think it's worth running the math on for you to see it. Yes, sir?
Could they give us the angle of that ramp and ask how long, like how far along the
That's
ramp?
exactly what I would be worried about. Is how would they phrase it? How high above the ground does it go along the ramp? How far along the ramp does it go? We know that H over, let's say L, equals sine of theta. So they're all related. They ask one, they're asking all. So they could ask how long along the ramp it goes. The ball has energy mgh, right? Now, how many of you are really paying attention right now, and how many of you need a break of your brain for a second before I go on? Because I'm going to ask something hard. So let's take a little. And what I'm about to say, you are better for it. Let's start at the bottom for just a minute and consider that I can calculate the amount of work done in getting the ball up this ramp. Okay? So, first, there's a lot of ways to get the ball up the ramp. One way was to have kinetic energy when I get here. Thus, the launcher, correct? So, the ball is brought to rest because gravity does work on the ball. And let's calculate the work done by gravity on the ball. The ball's going to travel this distance, L. Correct? Let's put the ball in the middle for just a minute. I'm going to ask you to make a choice, even though we're going to do both. Do you want me to talk about the component of the weight down the ramp, mg sine theta, or do you want me to just talk about the weight, mg? Doesn't matter which of these we choose. Let me tell you, because you guys know things now. You're smart. Mg sine theta does negative work on the ball. Right? The ball goes up the ramp at distance L. Mg sine theta is pointing down the ramp. The work done would be mg sine theta. That's what this is, mg sine theta, times L, times the cosine of 180 degrees. The ball's going this way, but the force acting on it is that way. 180 degrees, right? Which makes this negative mgl sine theta. Now it has to be negative. The work done by gravity slows the ball down. That's why it has to be negative. Everybody okay so far? Now, this part should not blow your mind, but sine theta equals h over L. So L sine theta equals h. We're not surprised, right? The ball's h above the ground. Are we okay? Not surprised? Good. Keep that in mind. This part might be more difficult for you to swallow. Look, the truth is, I should be able to use force times displacement times the cosine of the angle, and I should be able to use it holistically, meaning this is mg. Okay? So the work done by gravity will be, not F, but mg. Delta x is L. What is theta here? It's not the ramp. Theta is this angle. For cosine in my work equation, that's the angle we're talking about. Well, there's two ways to write it. Yes, sir?
You just do 90 plus theta?
90 plus theta is the way I would say. If you don't know why, think about the picture, guys. If I drop a perpendicular here, this is a right angle, and that part's theta, 90 plus theta. You could also have done 180 minus theta. You get the same idea. But 90 plus theta is the one I want you to use. Now, here's the thing. Oops, that was too many takeaways. Here's the thing. Cosine 90 plus theta. I don't know if you guys know this or not, but it's minus sine theta. Now, I don't think many of you know all of your trig identities, but I can tell you this. Cosine of A plus B. How many of you know this one? Anybody know this one? You guys will. So you guys are in calc now, right? The pre-calc folks are still learning this stuff then. But there's one you're going to learn about this one. I could show you another way, but it's not worth the time. Cosine of A plus B is cosine A cosine B minus sine A sine B. It's a trig identity you're going to learn. You're going to learn it pretty soon, actually. That's what all that unit circle work leads to eventually. Now, if you pay attention to this, this is cosine of 90 plus theta. 90 plus theta. So, wherever I have an A, I've got to put 90. Wherever I have a B, I got to put theta. What's the cosine of 90? 0. That's right. So that whole thing goes away. What's the sine of 90? 1. So cosine of 90 plus theta equals negative sine theta. So if you're really paying attention, the work done by gravity equals mg L sine theta, or mgh. So it doesn't seem to matter how I do my trig and how I do my physics. We are always going to get the same answer. You guys understand, all of this has to work this way, right? It has to. We can't get two different answers for the same situation. So if you want my takeaway from this, look, if something goes above the ground, figure out how far above the ground it goes. Amount of potential energy, mgh, period. Whether I shoot it up into the air or it goes up onto a ramp. Now, to be honest, all I have to do is say the dreaded friction word, and then we got differences, don't we? But I'll be honest with you, we're missing something huge here. Huge. And none of you will know this because none of you have had physics yet. But the ball is rolling. Rolling's its own form of energy. But we'll save that for second semester. We'll assume all of these are frictionless and the object's just sliding. I spent at least a moment of time talking about the importance of the word rate. And anytime I bring up the word rate, you should take notice because it's a per second, right? Rate is always about how long it takes for something to happen. The rate at which your displacement changes, velocity. The rate at which your velocity changes, acceleration. I've brought the word rate up quite a bit, and I'll continue to do so. The rate at which work is done is the name of power. It's also the rate at which energy is consumed. So what is power? It's work over time. It's a change in kinetic energy over time. It's a change in potential energy over time. It's energy used over time. That's power. Units, joules per second, which is also known as a watt. That's what power is. You'll notice all the stuff we've had about energy, I've never asked how long it takes for the object to get shot, how long it takes to go up into the air, how long it takes to roll down the ramp. We never asked how long anything takes. Energy is really good about telling us how fast something's going, how far it compresses something, how high it goes. Not so good about telling us how fast things occur. Power brings that element back. But here's the thing. Your definition of power and your definition of powerful will confuse the idea. Power does not tell you how powerful something is. Your definition of powerful suggests how hard something can push or pull. You think of powerful people being able to lift heavy things. Powerful, locomotives. You hear that word a lot. Be careful. Knowing something's power does not tell you how much force it applies. It tells you how fast it does work. So a car that has a lot of power can get up to speed quickly. It doesn't mean it can pull a boat. So I don't buy a Corvette to pull a boat, because a Corvette doesn't necessarily pull really hard on things, but it can change the Corvette's velocity quickly. If I want to pull a boat, I don't necessarily need to go fast. I need to pull something that's heavy. So be aware. Saying that a motor is powerful isn't saying it can lift a piano. It's saying the things it can lift, it can change their potential energy quickly. But you can have a powerful motor not lift hardly anything, but just lift it really fast. Does everybody understand the difference? So those are the things I'd like you to know about power. I do want you to be smart enough to know that our definition of work allows for flexibility in how we define power. You guys are pretty smart, right? Yes, you are. I can multiply and divide in any order I like. So if I decide to multiply and divide in this order, I would get force times delta x over t times the cosine of the angle. And what is delta x over t? Yeah, it's the rate of change of your position, so it's velocity. Force times velocity is another way to calculate power. So, for the tiles being pushed up to the top of the building by the elevator, you might want this version of power. The force is the weight of the tiles, power is the engine. That's how you can figure out how fast they're going up to the top of the building. The first thing I want to point out about this, the idea of using a spring here, And this, I get the idea that I've not talked about it. That doesn't change to me the fact that you guys could benefit from cracking open the book and looking through it a little bit. That's why you have one. Let me start out by just talking about the concept of elastic or spring. All of these words really speak to the same thing. The elastic force or a spring force or a restoring force. They all speak to the same thing. The concept is quite straightforward, that there are several types of materials out there that when you attempt to change their shape, they will attempt to return back to their original shape. So a spring is a very visual kind of representation of that. If you pull back a spring, and hold it there, the moment you release it, there will be a tendency of the spring to attempt to return to its original shape and size. A rubber band. You stretch out a rubber band, it will try and return to its original shape and size. Is that a pretty obvious idea? Do I have to really demonstrate that anymore, talk about it more? All right. We call this a restoring force. Not all restoring forces are the same. So we are going to focus on what's known as a Hooke's law restoring force. Because most restoring forces in simple physics obey Hooke's law. Hooke's law is a simple proportionality. And based on Hooke's law, the more you change an object's shape, the larger the force is to return it to its original shape. In a Hooke's law restoring force, the more you try and change an object's shape, the bigger the force will be to return it to its original shape. That's a lot of words. So based on what I've drawn here on the side, consider that if we displaced the spring a distance x, the force from the spring would be proportional to x. That's Hooke's law. X represents how much the spring was compressed. F is the force from the spring attempting to return it. Notice in this proportionality, as you increase X, you increase the force. Hooke's law is a direct proportionality. Now, to be complete, we need to recognize that X is a vector. I can push in on the spring or pull out on the spring. Force is also a vector. To be clear, we have to make sure we put a negative sign here. This negative sign is to remind you that if you compress the spring to the left, the force from the spring will be to the right. And if you pulled out the spring to the right, the force from the spring would be to the left. That's what makes this a restoring force. The force is in opposition to the displacement. Now that's Hooke's law. I'm not going to spend a lot of time talking about Hooke's law. It's not critical that you understand it for the next test. It will be critical that you understand it for the final exam. So I do want you to know, when it comes to calculating work, we can't use our definition to calculate work. Not when it comes to a spring. And the reason is because our definition of work has always relied on a constant force. And in this case, it takes an ever-increasing force to compress a spring. So our rules won't work. We need calculus, actually. So I will just tell you without proof that the work done in compressing a spring is minus 1/2 kx squared. Which means elastic potential energy is 1/2 kx squared. Now, I'm really right now talking just to the people who pay attention closely. I know those look exactly the same. But remember, the work done by gravity when you lift something was negative, because you are working against gravity, while gravitational potential energy is always considered positive. So this is true for anything that stores energy. The work done while storing that energy is negative, so that the energy stays with the object. That okay, guys? You see that in the back now?
Thank you.
No worries. So let's go to that problem you were talking about. In that problem you were talking about, there's a spring launcher, and I'm going to draw several different states of the spring launcher. By spring launcher, it's like a little spring gun. I don't know if you guys have ever seen these. They sell them typically around the holidays. These little ping pong ball launchers. It's just got a little spring in it. You can launch a ball with it. You guys know what I'm talking about? This thing that we used for the projectile motion quiz is this. Remember where you pushed the spring in, put the ball in there, and shot the ball? So that's the first state of the system, was a state where we compressed the spring and dropped the ball in there. In the problem, the spring was compressed 25 centimeters, or 0.25 meters. The spring was then released, and when the spring was released, it did work on the ball to speed it up and give it some velocity, so that later in the problem, the ball would have gone up into the air and reached its highest point above the launcher. Why? So again, I want to make sure you all understand that I am setting the reference level for this problem at the lowest position the ball attains. I'm going to set this as 0. Now, the way I see it, this problem has 3 parts. Part A, B, and C. And by parts, I don't mean parts of the problem. I mean places to observe what's happening to the energy. There's intermediates too, but these signify the 3 places the problem kind of identifies. If there's nothing to take energy out of the system, then the energy at A has to equal the energy at B, which also has to equal the energy at C. Now, as we've been talking this week, we've been talking about gravitational potential energy, kinetic energy, and now elastic potential energy. And I know I wrote that on the bottom of the screen, but it's something you should already have in your notes. I'm just putting it down there so that we have reference. But it's just the three relationships: gravitational potential, elastic potential, and kinetic. At points A, B, and C, our energy can be in any one or all of these forms. When trying to determine what type of energy your system has, just ask yourself, is the object pushed back against a spring? Is the object above the reference level? Do you think the object is moving? This should help you ascertain what forms of energy exist at each point. For example, looking at situation A, is the object moving? If it's not moving, there's no kinetic energy. Is the object above the reference level? No, it's at the reference level, so there's no gravitational potential energy. Is the object in cooperation with a spring or a piece of elastic? Yes. So at that instant, there is elastic potential energy. Move on to B for a minute. At B, is the object moving? Yeah, it's being shot out of the spring launcher. Pretty sure we can assume it has velocity. Is the object above the reference level? Yes. Not much, but it's above the reference level. Is the object compressed a spring? No, the spring is now in its relaxed state. Keep moving on. Part C. Is the object above the reference level? Yeah. Is the object moving? Not at its highest point. Is the object pushed back against a spring? No. Let's be careful about dealing with potential energy. The gravitational potential energy is how high the object is above the reference level. Again, the problem wants me to just put y here, but that's not true. It's y plus 0.25. All of these amounts of energy have to be equal because we're dealing with a situation in which no other external forces are here to take energy out of the system. So if I know the energy at one of these locations, I know it at all. Now, to answer this question or do this problem, I would have to be given enough information to complete one of the states of the problem. I know they told me the mass of the ball is 1.5 kilograms. It's a pretty heavy ball. They tell me the spring constant is 667 newtons per meter in my version of the problem. I don't know if you guys have the same version or not. They told me that X was 0.25 meters. So that kind of tells me that at A, I can kind of figure out how much energy is in the system. I know the spring constant. I know how much the spring was depressed. And I have a formula for the energy stored in a spring. Just as an aside, lowercase k is a symbol for spring constant. I didn't say that earlier. The units are newtons per meter. The spring constant tells you how strong your spring is. Stronger springs give you more force per meter. So, Slinky, it's going to have a really low spring constant. Doesn't take much force to stretch a sprinkly, stretch a slinky, a sprinky. So the springs on your car, probably pretty high. You know, you can put hundreds of pounds in them and the cars don't change their height above the ground very much. So when we consider spring constants, the bigger the number, the more force it takes to change its shape. I'd argue that for most stuff in like a laboratory that you could interact with, hundreds of newtons per meter is probably appropriate. If you get one that's tens of thousands, it's a really, really strong spring. All right. Now, I don't think there's a whole lot left to talk about here. If I wanted to know how fast the launcher was launching the ball, do you realize I would just need the mass of the ball here? And they tell me it's 1.5, so 1/2 times 1.5 v squared plus 1.5 times 9.8 times 0.25. Notice the mass is not going to cancel out whenever you're using a spring. It only worked out because gravity and kinetic energy have mass in it. Most forms of energy don't have mass in it. Look, I'm not going to do the math here. Solving for V is not very interesting to me. Now, if I wanted to figure out Y, I don't need to know V to figure out Y. I don't have to look at this and only this. I can say that 1/2 kx squared equals mgh. Since the energy is equal everywhere, I can set any two states equal to each other. I don't have to go through a middleman. So since I know the energy at A, I know the energy at C. Now, are there any questions about that so far? Now look, they wanted you to set the reference level artificially at some other level. Well, there. And there was no reason to do that. And it's still disappointing because if they wanted the reference level to be there, they could have changed the problem to do so. But if you want to be an honest person about this problem and understand physics, then by setting the reference level there, you're suggesting the ball has negative potential energy here. And that's just not how physics works. They were trying to take a shortcut, and you just can't. On the other hand, what they really would like you to have known in this problem is to have only elastic here, only kinetic here, and only gravitational here. But that's just not what this problem states. If I wanted to make this problem, which was actually on last year's test, I've written a lot of tests before. If I was trying to isolate the energies so that I didn't have a mix of gravitational potential and elastic at the same time, like in this problem, it would not have been hard to do so. And all I would have had to have done is turn the spring on its side and put a little ramp over there. Right? Do you realize that if I did this, I could put the ball here, pull it back 0.25, and then the ball would be launched by the launcher and the height of the ball would not have changed. It would have left here with kinetic energy and then made it up the ramp and went to some height and now has nothing but gravitational potential. That would have isolated each form of energy. And there's nothing wrong with that. That would have been great. So that's how I would have done it if I wanted to isolate the three forms so they're not having two forms at once. So I'm not trying to trick you. I think the book was trying to oversimplify something that wasn't as simple as it looked. In fact, if I really want to do this and make it more, I think, our level of work, I would have done this. Truth is, I shouldn't use a ball at all. I should use a block, because if you use a ball would roll. Rolling is a different kind of kinetic energy. We're not going to cover that ground right now, but just be aware there's other pieces here that we're not talking about yet. So in order to simplify it and make it as generic as possible, I'd probably do it this way. Now I'm bringing this example up because I have a very good reason for it, a very valid reason, it's going to be on a test kind of reason. So for those of you who sweat and cry over tests, this is worth talking about. Would you all agree that the box is likely to go someplace along this ramp? Now, what I want to talk about next is actually kind of hard. And if you haven't recognized it right now, to understand where I'm going with this, there's a subtlety to the way in which this problem could be asked. If we say that I'm going to pull the box against the spring and release it, do all of you kind of agree that the box could go shooting up this ramp and will eventually come to rest somewhere up the ramp? Is that not a big deal? And let's just, for argument's sake, kind of indicate that at this point right here, the object would have its maximum velocity. In fact, whatever the velocity is along this area is likely to be the same until it starts going up the ramp. And as it starts going up the ramp, it's going to slow down. Does that make sense? It's going to slow down, of course, because gravity's doing work on it. Now, here's what I want you to consider. What would they ask? Would they ask how high above the ground the box goes to? Or would they ask how far along the ramp the box goes to? Now, I think all of you are not too, concerned about this. I want to use something other than theta for right now. Is that okay? That's why I used a different Greek letter. And the reason I'm bringing this first part up, this is the simple part, that you guys know that there's a relationship here. Right? You guys are aware that whether I ask what the height is or I ask what L is, they're really asking the same question. They have to be related because of the triangle. So if you know one, you know both. Does that make sense? In fact, I'm just going to write this off to the side that H equals L sine theta. That okay? All right. I want to talk to you about work for just a minute. If the box hits the ramp with some kinetic energy and slides up the ramp, as it's going up the ramp, gravity is going to be slowing it down. Would you all agree that there's a force of gravity down the ramp? How much is the force of gravity down the ramp? Go ahead.
Negative mg, the distance, times sine theta.
I just want the force part. You gave me a little more than I needed, but I just want the force part, which is mg sine theta. This is the component of the force down the ramp. So in calculating the work, 3 buckets. Cosine theta. I'm leaving it as theta right now. I'll have to figure out what that angle is in just a minute. The box is going to go a distance L up the ramp, but the force of gravity acting on the object as it goes up the ramp will be mg sine theta. I'm sorry, not theta. Sorry, guys. I even told you I was going to use a different symbol and totally didn't. just to screw with you, I guess. I'm sorry. I made a mistake. It is November 20th at 3:18. Mr. Shelton made a mistake. It's on the video now, so it's there forever. I don't know if I told you guys this, but here. So here we go. I want you to first understand that when we calculate the work here, I have mg sine phi times L times the cosine. Now this angle is the angle between the direction the box travels along the ramp and the direction of the force acting on the box. So the box is going this way along the ramp, and that would be the angle between its displacement along the ramp and the force acting on it. And I think we all can say that that is 180 degrees. Good so far? Well, do you all see then that this is negative mg L sine phi? We all okay so far? Now you might want to ask yourself why it's negative, but I'll remind you why. This work is changing the kinetic energy of the box. It's the reason the box is slowing down. At the top of the ramp, how much kinetic energy will the box have? 0. So up here, kinetic energy final equals 0. At the bottom, it's going to have kinetic energy, right? I don't know how much, whatever the spring gave it. That's the initial kinetic energy. This has to be the change in kinetic energy of the box, which will be K final minus K initial equals minus mgl sine phi. Do you all see that since this is 0, it's going to say that the initial kinetic energy equals mgl sine phi. We all seeing that okay? Well, remember, L sine phi is h. This is saying that the kinetic energy at the bottom is equal to mgh. Not a surprise, right? Conservation of energy. That the box's kinetic energy here will equal the gravitational potential energy there. So whether we talk about the work done along the ramp or just how high the box makes it, we're talking about the same amount of energy. Now, for you smarty smarts, it's a simple machine. That's what simple machines do. They exchange force for distance for the same amount of energy. We talked about that a month and a half ago. So whether we go up the ramp or jump straight up to h, it's the same amount of energy. All right, now, I know you're not going to like what I'm about to say. That wasn't the hard part. That would be the middle level part. So for those of you who are wondering, wow, that wasn't so bad, give it a sec. Okay? Let me talk to the really smarty smarts for just a minute. And some of you who don't think you're very smart actually pretty much are. I've discovered that this class, although it makes me crazy, has the smarter people in it. So, although you make me crazy, you guys consistently score pretty high. So I want you to think about this for a minute. Gravity is actually acting in this direction. Although we broke it up into a component, we don't have to. That's not what the definition of work says. So although all of this was about comparing it to kinetic energy, the truth is all I cared about was getting this. Aw. Sorry. But that's the end. I did this in 6th period, though. I will post it. Just so you know, we're going to talk about doing the work based on that angle next. Well, yeah, because this would be 90 and this would be theta. Well, plus phi. I'm sorry, plus phi. Did it- Okay. Well, if you look at this trig identity, and you're all supposed to, be able to look at it, you'll find that cosine of 90 plus phi equals negative sine phi. Which means that this is the same as this. Well, I could have, but most people don't know that cosine of 90 plus phi is equal to negative sine phi. What's that? I don't doubt it. That doesn't mean that people paid attention to that.